This CATL sodium-ion battery operates at -40 degrees Fahrenheit, where every lithium cell on the market shuts down cold. It costs up to 30% less per kilowatt hour to manufacture than lithium iron phosphate. Yet, despite sodium-ion chemistry being understood since the 1970s, the entire energy storage industry was built around one metal most of us can't afford. It's called the Naxtra battery. By the end, you'll know what it is, how it works, and what it saves you. Let's dive in. Right now, if you have a home battery system, or you've been quoted for one, there's a very good chance it runs on lithium, specifically lithium iron phosphate or lithium nickel manganese cobalt. And on paper, those chemistries look fine. They've gotten cheaper over the last decade. They're reasonably energy dense. Every installer in the country knows how to wire them. But the moment you pull back the curtain on what lithium actually costs you over 10 or 15 years, the picture changes fast. The average residential lithium iron phosphate battery pack in the United States retails between $800 and $1,200 per kilowatt hour, fully installed. That means a modest 10 kilowatt hour system runs you somewhere between $8,000 and $12,000 before any federal tax credit. And that tax credit, under Section 48E of the Inflation Reduction Act, only applies at the full 30% if the system is charged by solar. If you want standalone backup power charged from the grid, the IRS limits what you can claim. So, right out of the gate, the incentive rules push you toward a more expensive total package, not the simplest one. But the sticker price is only the first problem. Lithium batteries degrade. Every charge cycle shaves a tiny fraction off your total capacity. Most manufacturers warrant 80% capacity after 10 years or 6,000 cycles. That sounds decent until you do the math. After a decade, your $12,000 system stores only 8 kilowatt hours instead of 10. You paid for 2 kilowatt hours you no longer have. According to the National Renewable Energy Laboratory's 2022 degradation modeling study, real-world lithium iron phosphate cells in hot climates like Phoenix or Houston can lose capacity faster than the warranty curve predicts, because sustained ambient heat above 95 degrees Fahrenheit accelerates electrolyte decomposition. And if you live somewhere cold, the problem flips. Lithium iron phosphate cells start losing discharge capacity below 32 degrees Fahrenheit. By the time you hit -4, most packs are throttled to half their rated output or less. At -20, many shut off entirely to protect themselves from irreversible internal damage. The Tesla Powerwall 2, for example, lists an operating range of -4 to 122 degrees Fahrenheit, and its discharge rate drops significantly toward that lower boundary. A battery that quits when the furnace needs it most is not backup power. It's an expensive box in your garage with a warranty card. And when you see what sodium does at those same temperatures, you'll understand why the world's largest battery manufacturer just bet its entire production strategy on a different element. But first, you need to understand why the element they chose is nearly impossible to control or restrict. Here's what the lithium supply chain doesn't want on your radar. Lithium is not rare in a geological sense. There's plenty in the Earth's crust. But extractable lithium is concentrated in a handful of countries. Over 60% of global lithium refining runs through China. Another large share comes from brine operations in Chile and Argentina that face water use restrictions and political uncertainty. Australia mines the hard rock spodumene, but most of that ore ships to Chinese processing facilities anyway. The result is a supply chain that can be squeezed. Between 2021 and 2022, lithium carbonate spot prices spiked from around $10,000 per metric ton to over $70,000 per metric ton, an increase of over 400% in barely 12 months. That spike hit every battery manufacturer on Earth. It hit every customer quoted for a home battery, and it had nothing to do with the chemistry working or not. Now, if you're thinking that's just a temporary market blip and prices stabilized, you're partially right. Spot prices did fall through 2023 and into 2024. But the United States Geological Survey's 2024 Mineral Commodity Summary still lists lithium as a critical mineral with significant import reliance. The structural vulnerability never left. The moment demand surges again from electric vehicles, grid-scale storage, or military procurement, that same bottleneck tightens overnight. Sodium doesn't have that problem, and the reason why is as simple as the shaker sitting on your kitchen table. Sodium is the sixth most abundant element in the Earth's crust. It's dissolved in every ocean. It sits in rock salt deposits on every inhabited continent. Global soda ash production exceeds 60 million metric tons per year across dozens of countries, with major deposits in the United States at the Green River Basin in Wyoming, the largest natural trona reserve on the planet. The raw sodium carbonate costs roughly $1 to $3 per kilogram, compared to lithium carbonate, which, even at its 2024 lows, runs $15 to $20 per kilogram. You could not create a meaningful supply chain choke point for sodium if you tried. There is simply too much of it, spread across too many nations, accessible with mining and evaporation methods humans have used for centuries. The chemistry itself works on the same intercalation principle as lithium ion. You have a cathode, an anode, an electrolyte, and a separator. Ions shuttle back and forth between the cathode and the anode during charge and discharge. In a lithium cell, those shuttling ions are lithium. In a sodium cell, they're sodium. The electron flow through the external circuit is what powers your inverter, your lights, your refrigerator. Think of it like two sponges separated by a membrane, with water flowing between them. In a lithium battery, the water comes from a mineral spring controlled by 3 countries. In a sodium battery, the water is the ocean. The reason sodium ions behave so differently at extreme cold comes down to ionic radius and electrolyte engineering. Sodium ions are larger, roughly 1.02 angstroms, versus lithium's 0.76 angstroms. That larger size is a disadvantage for energy density, because fewer ions pack into the same cathode volume. But the electrolyte formulations CATL engineered specifically for the Naxtra line maintain high ionic conductivity at temperatures that turn lithium electrolytes into a sluggish, near-frozen gel. CATL's published specifications state the Naxtra cell retains over 90% of its room temperature discharge capacity at -4 degrees Fahrenheit. At -22 degrees, it still operates above 80%. At -40 degrees, it delivers functional output that no lithium iron phosphate cell on the commercial market can match. Not Tesla's Powerwall, not BYD's Blade battery, not Enphase's IQ battery, not the Sonnencore, none of them. This is the performance gap that matters if you live in Minnesota, Montana, North Dakota, Maine, Wisconsin, Alaska, or any state where the thermometer parks below zero for weeks at a stretch. Your lithium battery is either derated to a fraction of its nameplate capacity or shut down entirely. A Naxtra sodium-ion cell in the same garage keeps delivering power. And wait until you hear the next difference, because if your battery sits inside your home, behind drywall, near your family, this one matters more than efficiency or cost. Lithium-ion batteries can enter a state called thermal runaway. It is a self-reinforcing exothermic reaction where the cell overheats, the internal polyethylene separator melts, the cathode decomposes, and temperatures spike past 1,000 degrees Fahrenheit in seconds. One cell in thermal runaway heats the adjacent cell past its critical threshold, triggering a chain reaction that can consume an entire pack. These fires burn with extreme intensity and can reignite hours after apparent suppression. The New York City Fire Department responded to over 260 lithium battery fires in 2023 alone, primarily from e-bike and e-scooter packs, but involving the same lithium-ion chemistry family used in home storage. The National Fire Protection Association updated NFPA 855, its standard for stationary energy storage installations, specifically because lithium battery fires demand different suppression protocols, longer cool-down monitoring, and greater setback distances from occupied structures. Sodium-ion cells do not experience thermal runaway. The cathode materials used in sodium-ion chemistry, typically Prussian blue analogs or layered transition metal oxide structures, are thermodynamically more stable at elevated temperatures. Their decomposition onset temperature is significantly higher, and the reaction releases less energy when it does occur. CATL has published nail penetration test results, where a hardened steel nail is driven completely through a fully charged Naxtra cell. The cell did not ignite, it did not vent flame, it did not propagate failure to neighboring cells. For a battery mounted on your garage wall, in a house where your family sleeps upstairs, that difference is not a spec sheet footnote. It is a safety margin measured in lives. Now, if you're thinking this sounds compelling, but it must be unproven laboratory technology, the timeline tells a different story. Sodium-ion battery research dates back to the late 1970s. Researchers at the University of Oxford, working in the same inorganic chemistry laboratory where John Goodenough and Koichi Mizushima developed the lithium cobalt oxide cathode that made modern lithium-ion possible, also explored sodium intercalation compounds in layered metal oxides. The physics was understood. The electrochemistry was demonstrated in working cells. But the consumer electronics revolution of the 1990s needed the smallest, lightest batteries possible for laptops and mobile phones. Energy density was the only metric that mattered, and sodium couldn't win on that axis. So, for nearly 4 decades, sodium-ion sat on the shelf, while lithium attracted every research dollar, every manufacturing line, every policy incentive, and every venture capital check. The Argonne National Laboratory in Illinois, one of the Department of Energy's premier research facilities, published a comprehensive techno-economic review in 2021, concluding that sodium-ion technology had reached commercial viability, but lacked the manufacturing ecosystem lithium had built over 30 years. The science was never the barrier. The barrier was an entire industry architected around one element. And that architecture is now costing you thousands of dollars every time you install a home battery. CATL, Contemporary Amperex Technology Company Limited, headquartered in Ningde, Fujian Province, China, is the largest battery manufacturer on the planet. They produced roughly 37% of all electric vehicle batteries sold worldwide in 2023, according to SNE research data. When a company at that scale commits to mass production of a new chemistry, it is not a press release, it is a tectonic shift. In 2023, CATL unveiled the first-generation Naxtra sodium-ion cell with an energy density of 160 watt-hours per kilogram. For comparison, most lithium iron phosphate cells land between 150 and 180 watt-hours per kilogram. The density gap is already narrow. CATL has publicly stated their second-generation Naxtra cells will exceed 200 watt-hours per kilogram, closing it almost entirely. The company broke ground on dedicated sodium-ion production lines in Guizhou and Jiangxi provinces through 2023 and 2024. Chery Automobile's iCar brand launched vehicles equipped with sodium-ion battery packs for retail sale on the Chinese market in 2024. These are not concept cars. They are mass-produced vehicles on dealership floors, being driven through real winters by real customers. CATL is not the only company moving. High-NA Battery, a spin-off from the Chinese Academy of Sciences, founded by Professor Hu Yongsheng, installed a 1 megawatt-hour sodium-ion energy storage station connected to the grid in Shaanxi Province in 2023 for peak shaving services. Faradion, a British company now owned by Reliance Industries of India, holds over 40 patents on sodium-ion cathode formulations and demonstrated a fully operational electric scooter running entirely on sodium-ion cells. In the United States, Natron Energy completed its manufacturing facility in Holland, Michigan, in 2024, producing Prussian blue sodium-ion batteries for data center backup and industrial applications. Natron's published cycle life data exceeds 50,000 full charge and discharge cycles. To put that in perspective, A lithium iron phosphate cell warranted for 6,000 cycles over 10 years sounds solid. A sodium-ion cell doing 50,000 cycles in a stationary application could theoretically operate for decades before needing replacement. That is a fundamentally different ownership equation. And this is where the economics shift permanently, because a battery that outlasts the roof above it rewrites every cost calculation you've ever been given. So why can't you walk into Home Depot and buy a sodium-ion home battery today? The answer follows the same structural pattern as every alternative energy technology that challenges the installed base. The entire home battery market in the United States is built around lithium. Every installer is trained on lithium systems. Every inverter compatibility chart lists lithium voltage profiles. Every product certification at underwriters' laboratories follows test protocols designed for lithium-ion chemistry. Sodium-ion does not yet have a UL 9540 listing for residential energy storage in the United States. That means even if a sodium-ion pack physically fits your existing inverter bracket and electrically behaves identically, your local building inspector can refuse the permit because the component lacks the required certification stamp. The UL listing process typically takes 12 to 18 months and costs manufacturers several $100,000 per product line. It is not a technical judgment about whether sodium-ion is safe. It is a procedural gate that takes time and money to walk through. Then there's the federal incentive framework. The investment tax credit under the Inflation Reduction Act provides up to 30% for residential energy storage paired with solar. The statutory language is technology neutral, referencing energy storage technology, without specifying lithium. But every installer worksheet, every IRS worked example, every financing product from lenders like Mosaic, GoodLeap, and Sunlight Financial is modeled on lithium-ion systems. No mortgage appraiser knows how to value a sodium-ion installation. Fannie Mae's Selling Guide, which governs how appraisers treat energy improvements, references solar panels and battery storage, but provides no valuation methodology for a chemistry the appraiser has never seen in a comparable sale. The system is not hostile to sodium-ion. It is structurally blind to it. And in a market where the homeowner needs a tax credit, a building permit, a past inspection, and an inverter compatibility certificate to bring a battery online, being invisible to the system is functionally identical to being locked out of it. The lobbying dimension is real but structural, not conspiratorial. The lithium supply chain spans mining companies, lithium refiners, cathode material producers, cell manufacturers, pack integrators, installers, and a growing recycling industry. That represents a multi-hundred-billion-dollar annual global ecosystem with trade associations, government advisory roles, and procurement influence. Organizations like the Battery Innovation Center in Newberry, Indiana, the Federal Consortium for Advanced Batteries, and the Zero Emission Transportation Association all participate in shaping Department of Energy procurement standards and Department of Defense battery specifications that reference lithium-ion performance metrics by default. Sodium-ion doesn't face open opposition in these forums. It faces the enormous inertia of a system that already wrote its preferred answer into every procurement document and building code years ago. Here is what you can do right now to position yourself. Sodium-ion home batteries are not yet available through mainstream American retailers, but the supply chain is building rapidly. Natron Energy's Prussian Blue sodium-ion cells are commercially available today for data center and industrial backup applications. Their Blue Tray 3000 is a rack-mounted system engineered for critical power environments. If you're building a workshop, agricultural, or small commercial backup system, contacting Natron directly through their Santa Clara, California headquarters is a concrete starting point. For hands-on builders comfortable assembling their own packs, Chinese manufacturers, including Haina and various CATL supply chain partners, offer sodium-ion cells in the 32-140 cylindrical format and the prismatic 280 amp-hour form factor. These are available through Alibaba, specialized battery importers, and domestic sellers like Battery Hookup. Current cell-level pricing runs between $60 and $90 per kilowatt-hour. Compare that directly to lithium iron phosphate cells from the same sources at $110 to $150 per kilowatt-hour. The savings at the cell level are 30 to 40%. To build a functional pack, you need the cells, a battery management system specifically rated for sodium-ion voltage curves, nickel strip or copper bus bar for cell interconnection, a spot welder or mechanical compression assembly, and a hybrid or off-grid inverter. Sodium-ion cells typically operate at a nominal voltage around 3.1 volts per cell, slightly lower than lithium iron phosphate's 3.2. More critically, the charge termination voltage and discharge cutoff voltage differ. Do not use a lithium BMS. The balancing algorithms, over-voltage protection thresholds, and under-voltage lockouts are calibrated for a different chemistry and will either undercharge the sodium cells or fail to protect them properly. Will Prowse, an independent off-grid solar tester with over 600,000 YouTube subscribers, has published detailed teardown and capacity cycle tests of early sodium-ion cells using his standardized bench testing protocol. His channel provides real-world discharge curves, internal resistance measurements, and cycle degradation data you can compare directly to his extensive lithium iron phosphate database. For sourcing guidance, the DIY Solar Forum has active threads tracking which sodium-ion cells and BMS boards members have tested successfully. Budget roughly $400 to $800 for a 5 kilowatt-hour pack at the cell level, before adding the BMS, enclosure, wiring, and fusing. A comparable lithium iron phosphate pack from the same import channels costs $600 to $1,000 at the cell level. The critical warning is this: do not buy sodium-ion cells without verifying the supplier's independent capacity test data at the 1C and 0.5C discharge rates. This market is new enough that mislabeled, recycled, or factory reject cells absolutely exist. If the supplier cannot provide discharge test documentation, walk away. A second warning applies to shipping. Sodium-ion cells can legally be shipped at 0 volts state of charge, which actually simplifies transportation regulations compared to lithium. But confirm with your freight forwarder that the cells meet IATA and DOT shipping classifications before ordering. There are real limitations to acknowledge honestly. First, sodium-ion batteries have lower gravimetric energy density than lithium. For the same 10 kilowatt-hour capacity, your sodium-ion pack will be physically larger and roughly 20 to 30% heavier. In a stationary home application where the pack sits on a garage floor or mounts to a wall, that translates to maybe 40 extra pounds and a few extra inches of depth. It is a minor inconvenience, not a deal breaker. In a vehicle or portable application, the weight penalty matters more, which is why the automotive rollout is starting with urban commuter cars rather than long-range highway vehicles. Second, the manufacturing ecosystem is still ramping. Prices will continue falling as production volumes scale through 2025 and 2026, but right now, the number of plug-and-play residential sodium-ion products with UL certification available through American distributors is effectively zero. You are either an early builder willing to assemble and test your own pack with the right BMS and inverter, or you are waiting 12 to 24 months for certified turnkey products to reach the American retail market. That is the honest timeline. The choice sitting on the table right now is this. A lithium iron phosphate home battery costs $8,000 to $12,000 fully installed, degrades to 80% capacity in 10 years, shuts down or severely derates in extreme cold, and carries a documented fire risk that fire departments across the country are training specifically to handle. A sodium-ion battery built from the same element as the salt on your dinner table costs 30% less at the cell level, operates at full capacity at -4 degrees Fahrenheit, delivers functional power at -40, physically cannot enter thermal runaway, and at 50,000 cycles could outlast every other component in your electrical system. CATL, the single largest battery manufacturer on Earth, is mass-producing them on dedicated factory lines right now. The Naxtra cell holds over 90% capacity at a temperature that would brick every lithium home battery currently sold in America. And the only reason you cannot buy one at your local hardware store this afternoon is that the certification pipeline, the federal incentive structure, and the installer training ecosystem were all built on the assumption that the battery chemistry would always be lithium. That assumption is cracking. Within 3 years, the installed cost gap between a sodium-ion and a lithium home battery system could reach 40%, saving a typical homeowner $3,000 to $5,000 on a 10 kilowatt-hour installation. If you want to power, heat, and cool your home off-grid, the Passive House files show you how. Full plans, exact materials, and the honest numbers nobody else gives you.
It's not too late to start lowering your bill. Scan the QR code and see for yourself.
So here is my question for you. If a fully UL-certified sodium-ion home battery hit the American market tomorrow at 30% less than a comparable lithium iron phosphate system, would you buy one based on the published specs alone, or would you hold off for 5 years of verified field data from other homeowners first? I'd genuinely like to know which way you'd go, so drop your answer in the comments. If this kind of breakdown is useful to you, subscribing and sharing is the single best way to help this channel keep producing them. Next time, we're digging into a compressed air storage system built from a salvaged propane tank and a scrap compressor that banks energy with zero chemical degradation, and the cost per stored kilowatt hour is going to make both lithium and sodium look expensive.